Hey there, welcome back. Today, we're going to turn this motion into this action in software. Let's get to it. I've got an idea. I want to water my plants when I'm away from the house. Let's say I'm on vacation. I want to be able to send it commands to be able to water when I decide, maybe have some sort of a schedule, and I'd like to know how much water is left in the reservoir. So I decided what I'm going to do is I'm going to attack this from the reservoir side first and then work up through scheduling and pumping and all of that. Today, I want to talk about the reservoir itself and how we know how much water is in it. So I'm going to use a 5-gallon bucket. So I looked around online and I found this. This is a fuel tank level sensor. We've got a wire here. It's got 2 wires on it. It's got some sort of a sensor thing here. It's got a float that moves up and down. The instructions that came with this are very, let's call them scarce. Basically, it just tells you what the resistance is and not to exceed 1/8 of a watt. That's all it gives you. So how do you go from something like this to software? I'm going to talk about the procedure that I go through to take just some arbitrary unknown sensor and make that into a driver in C# that we can then use in our application. So let's go take a look at the datasheet that came with this, and datasheet is a very loose term. Let's also take a look at how I analyzed the data that comes out of this and turned it into software. This thing turned out to be not near as straightforward as I was hoping, so there are some interesting lessons to be learned. So here are the instructions that came with this, and I say instructions very loosely. Basically, it's one sheet, nothing on the back, and it's just some wiring diagrams for sensors that have different numbers of wires. Looks like they make these with like high alarm, low alarm, high and low, whatever. None of this applies because mine's just a 2-wire sensor that gives us a resistance. If we take a look up here, doesn't say anything about resistance. It does say what the hole size is, I guess, if you are looking to buy a bit. Not that you can't measure it, so I don't know that it's really all that useful. The one thing it does say that is of use, that is important, is it says that the rated power of the resistor used for the sensor is 1/8 watt only. Don't exceed that. So we want to make sure when we design the circuit to drive this that we don't exceed 1/8 of a watt. Really, that's the only thing that is really of any importance here. If we take a look at the end of the sensor itself, you can see right here it says 240-33. That's the only indicator that gives us what the resistance is, and if you didn't know that that was resistance, you'd be like, was that a part number? I don't know. But that's what this one is. They make some other ones that are like 1 to 190 or something along those lines, 1 to 290, I don't remember. The important thing is that we know the resistance range of this. If you don't have this number, it's not a big deal. We can do that with a meter, and I'm going to show you that here in a minute because it's interesting in its own right. So the first thing I want to do is I want to hook up a meter and just check the resistance on this. So I'm going to put this on 2K. I have it hooked up to the leads here. You can see it's about 240, so 243 ohms here to 34, and I believe it was 22 to 240, 33 to 240, yeah. So 33 to 240. Within margin of error of both the meter and the device. That's probably pretty close. So we know that this is a 33 to 240. While we're here, let's take a look at one other thing that took me honestly a lot longer than it should have to realize. I was expecting this to be both linear and kind of a continuous resistance as we change. But look, as I move this, so let's start here. Watch the resistance. So I moved quite a bit. It goes from 240 all of a sudden down to 140. Back to 240. There's no gradual change between those. So it's working with switches inside this thing. And then we move a bunch more. There's 130, 120. It's about 115, but you can see that it's quantized, right? So we've got these specific values that it hits. say here's 80, but there is no, where is there? There it is, 92, right? There is no between 80 and 92. There's no resistance in there. It just snaps from one to the other. Again, this has probably got some switches in it. This float spins, so there's nothing mechanical hooked up between them. So I'm guessing it's got some sort of switches in here. Maybe this has a magnet in it so that as it moves up and down, it triggers those. It's important to know, though, that it's not continuous. The other thing that's important to know is it is also not linear, right? So we go from 240 here to 140 just right here at the end. So we drop 100 ohms of resistance here, and then in roughly the same distance up here, we drop, what, 12 ohms? So it's a completely non-linear and quantized sensor. What that means is it is not easy to do a mathematical calculation to give you the resistance to the distance that you are here. And what I'm going to do is turn this into a percent full. So basically we're going to go from 0 here, a value, to a 100 here. So that's my goal, is to have the output of 0 to 100 based on the resistance. Let's go take a look at what we do for calculations and how we build the circuit. It's really simple, but we have to do a little bit of math to figure out what the circuit is to hook this up to our A to D on our YoshiPi. Let's go over the circuit design. There's going to be some math. I'm not going to do a lot of the math. I'll just kind of write out how we go from point A to point B. If you're interested in doing the math, you can go ahead and do the calculations, but we're just going to go from how you set it up to the answer. At any rate, we know that microcontrollers don't directly measure resistance. They have an analog input, which is a voltage, so we need to get a voltage from our system in and then turn that back into a resistance via calculation. We're going to do that with a voltage divider. So a standard voltage divider. We've got our source voltage here. I'm just going to go with 5 volt. We could use the 3.3. Doesn't really matter. It's the voltage that's available to us. We have one resistor. We'll call this R1. We have another resistor, R2. And if we measure right here, this output voltage is a function of these two resistors. The function, again, we're not going to solve this, but I'm going to at least give you the function. So if this is V out, and call this 5 volt, but let's just call this our reference voltage, Vref. So our V out is going to be our reference voltage times R2, this low side resistor, divided by R1 plus R2. So this is the voltage divider calculator. This here is going to be our analog input. This is, again, I'm going to go from our 5 volt. And then these two resistors, one of them is going to be a fixed known. So I'll typically put this as my fixed known resistor. And then this one is our sensor. So we know that this is somewhere between 33 and 240. 33 to 240. So given all of this information, we want to find a resistor for here that gives us an output that does not exceed 3.3 if we give it 5 volt in. So we know that we have a maximum of 3.3. And if we run 33 ohm, this is going to give a higher voltage than this. So we just have to solve it for the 33 ohm scenario. So the solution to this, we have our 3.3 as our output, right? 5 volt is our source. And this second resistor, 33 is our R1 plus R2. So that's how we take this formula and plug it in for a 3.3 volt output and 5 volt reference, and then the 33 ohm at the low side of this sensor. If we solve this, we come up with an R2 should be about 64 ohms. That's not a standard resistor. A standard one that you'd get in a kit is, say, 68 ohm. So we could say, well, let's put in a 68 ohm resistor. And if we run this calculation out, it comes out just below 3.3. So that looks good. However, if we come back and look at this circuit, and remember we had talked about that sensor says don't exceed 1/8 of a watt. What happens if, say, we have this hooked up and this, instead of going through this resistor, somehow gets grounded? So basically the power flows through this straight to ground, right? So basically we would have power coming through our sensor and direct to ground. Well, the problem with that is, and then again, this is just a simple Ohm's law calculation, right? Do that on another sheet. Ohm's law there. V equals IR. If we have 5 volts in, and we know that resistance is at, say, 33 ohms, what is our I? Well, we end up with about 150 milliamps running through that sensor. 150 milliamps, let's turn that into power. P equals IV. So our power is, our I is 0.150, and our voltage is 5. We're going to have roughly 3/4 of a watt. And it said don't exceed 1/8 of a watt. So if somehow we had it wired up and we made a mistake and touched this wire to ground, or the V out to ground, so if we had it just hanging there and we're going to plug it into our A to D, but we actually accidentally touch ground, we're going to drive 150 milliamps through our sensor, and it's going to burn up, and well, then you've got a garbage sensor. You have to order another one, and you've spent money that you didn't need to. So what we need to do is we need to adjust so that this doesn't happen. The easiest way to do that is to split this so we don't just have our sensor, but we have 2 resistors. So let's just take a look at what that would look like real quick. So we have our source voltage comes over, and what we would do is we would go through the sensor here. So here are the 2 wires for the sensor. And then we come through another resistor here. Then we have our low end resistor. And this goes to our ADC. So this is our float sensor, or, the tank level sender. And then we have another one here. And this is R2. So we have to add these 2 resistances together to get R1. Again, I promised I would not go through all of the math on this, but it turns out that if you use a 120 ohm here and a 47 ohm here, you end up not burning it up if you ground out, and you end up in a nice voltage range that doesn't exceed, I think, around 3 volts. That's the math that you go through in order to figure something like this out. So think about not just the ideal scenario, but what happens if inevitably you touch a wire to the wrong thing. Now let's go build this circuit. Not complex at all. Again, it's just 2 resistors. We've got the 47 here. This comes from our high side. So we've got power. It's actually going to go through the 47. Then I've got a screw terminal here. I'm going to hook the sensor up to this one. So we have a resistor that is the sender. Comes back in here. This is our A to D line. And then this is the 120, goes to ground. So we have 3 wires coming here. We've got our analog output, from the voltage divider, our power in, and our ground. And we've just got these hooked up to these screw terminals on the YoshiPi. Then I'll take the sensor and I'm just going to attach it to these screw terminals here. Because it's just a resistor, the polarity does not matter. You can hook it up like this, or you can flip the wires and hook it up like this. Doesn't matter. Up to this point, you could be doing this for any type of a platform. You could be writing in Python, C, Rust, whatever. I'm going to do this in C#, so let's go take a look at some code for how we use the YoshiPi to read this value. I have this tank level sensor. It's a 12-inch, 33 ohm to 240 ohm resistance sensor, and it derives from this resistive tank level sender. This implementation basically just has this table, and this is a lookup of the resistance to the fill level. Remember how I said it was quantized, so we have very discrete numbers and very discrete resistances. So we've got these resistance that equates to a fill level. The way I got these fill levels was I actually just measured it with the tape measure. So I think it was a total of 9.5 inches of travel, something like that. I just figured out where each one of these switches was and measured how much of the travel it was. So 95% travel down to 0. So when it is all the way at the bottom of the tank, we've got 250 ohms of resistance. When it's up at the very top or really close to the top, it's got 37 ohms. The reason it isn't 100 is because that switch isn't all the way at the top. So it's down a little bit where this one actually triggers. So let's go take a look at the base class. That's kind of where more of the work happens. The base class is very, very simple though. We have an event that is fill level changed for when it changes, and we have a single property that is the fill level percent. This will give you back 0 to 100. And again, it is just a lookup into this table. The sensor itself has several constructors, but basically we just take the input port, the reference voltage. Now on this one, what I did was I actually measured it. It says 5 volts on the silk screen, but they rarely are. On this Raspberry Pi Zero, it actually turns out to be about 4.65 volts. So I pass that in. You can see I'm not passing in anything else. So it uses the defaults of 47 and 120 ohms. Those are the ones that I had calculated. And then all we do is we tell it to start updating. Here, that starts reading the analog input. When it changes, it calculates the gauge resistance, again, using that voltage divider formula that we talked about. Here it is here, but this code is open source if you want to go take a look at it. It turns that gauge resistance into a fill level percent by using link to look into that map that we just saw. And so it's just looking at this and finding a number in this first column, finds whatever is the closest to the value that we read from the A to D, and then returns that percentage. That percentage gets set to the property, and then it gets fired out the event. So our application itself, there's a fair bit of code here. Most of it is just the drawing code. For this sensor, really, it boils down to just these 2 lines of code. We create the sensor. We tell it we want it on A00 for the analog input on the YoshiPi, and we have a reference voltage of 4.6 volts. Then when the fill level change happens, every time we get the event, we're going to call this set water level on the display. Set water level on the display just changes the height of the blue box that is the water level for that gauge. So if we go to take a look at running this, execute that. So when we move it, the gauge on the screen moves accordingly. That's it. That's all I've got for you today. Thanks for watching.